flow to Lake Edward, so to the Nile Basin. And after the elevation of this region, the lake began flowing to the south to Lake Tanganyika. So it's connected now to Lake Tanganyika and then belongs to the Congo River Basin. An important characteristic is the very large amount of methane that is produced in the deep waters. It is divided between two countries, one down this path, Congo on the western part. Presently, 2 million people live on the lake and depend on the resource of this lake and of the ecosystem production of the surface waters, so mainly the fisheries of the Limnolog, the Sambaza, which is called locally the Sambaza. The Lake Kivu has been studied for some time. For example, from the beginning of the 20th century, but the expedition at that time were mainly interested in inventories of the diversity, actually, and they noted for Lake Kivu a very poor diversity, about 30 species of fish at that time, which is very, very low compared to Lake Tanganyika, which is about 400 species of endemic fish, and Lake Malawi, for example, is even more. A man who studied Lake Kivu, the Lake Kivu hydrology, particularly Damas, who published this book here, so he proved different characteristics from Lake Kivu, including that there were a lot of large concentration of gases in the deep water. But he didn't know the nature of these gases that were studied, that were determined by other people like Kappa and Kukra. Other Belgians, these are Belgians, of course, Damas came from the University of Liège. André Kappa was the director of the Institute of Natural Sciences in Belgium. And he did the TEA mission in the 1950s, Kivu, Edward, and Albert, so on these 3 days. So there are a lot of information, but only ecological information, diversity, nothing on phytoplankton, nothing on cargo reproduction. So there were a lot of new knowledge to be acquired on this lake. So this lake is special in this way. So you have here the depth of the lake, about 500 meters, and then you have the concentration of various substances. If you look at the temperature, for example, which is this line here, temperature goes, the temperature scale is here, you have about 35 degrees, 34, 35 degrees. At the upper decline, from 60 meters, the temperature begins to increase, which is really atypical for us. You would expect the temperature will decrease as you go down the lake. Here, the temperature increases. With the increase of temperature, you see that oxygen, for example, is present only down to 60 meters. And if you study, for example, methane and CO2, you have these graphs here. So the lake actually is totally anoxic from 60 meters down to the bottom. So this is a very large anoxic zone in which you have a gradient of salinity. Salinity is here, homogeneous enteric salinity, and then it increases. There are 2 steps, 2 main steps of salinity in Lake Kivu. A first big step at 270 meters, and another step here. This increase of salinity causes an increase in density of the water, so that the gas which is produced by the volcanic inputs, actually this gas is from inputs of sublactate sources located at different depths, but the main sources are here and here. It's an input of CO2. This CO2 is transformed to methane by bacteria, by anaerobic bacteria. And this CO2 is transformed to methane, and 2/3 of the methane comes from the reduction of CO2. The rest of the methane, 1/3, depends on the use of the organic matter which is produced in the surface water, settled to the bottom. So 1/3 of the methane is produced by the decomposition in anaerobic conditions by anaerobic bacteria. And so this can be problematic because these lakes, which contain a lot of gas, they can be degazing, but this is another topic that I will talk about later. Let's talk about what is known about the productivity of the surface waters. So from the mission led by Kappa, the Clean Yield mission in the 1950s, we know that, that there was no fish in the surface water. And so there was the idea to introduce this sardine, Limnodon, in Lake Kivu. And this allowed the development of the fishery, but there were questions. One of the questions was posed by a zooplankton specialist, which predicted that the introduction of this fish, which is zooplanktivore, would actually cause an ecological disaster. So the question is the fishery of Lake Kivu sustainable? So there was a project which started, which was financed by the FAO, which was the ISABASA project, where this is a fishery unit that is used of Lake Kivu. This is night fishing. They use light to attract the fish to the surface with a net which is deployed below the boat, and at the end of the night they lift the net, and so they have a catch of fish, which is recorded here. Typical year is where data collected by the ISABASA project from the end of 87 to the end of 89, and you can see that the CPUE is the catch per unit effort, the catch per boat, for example. You can see that this is very variable. Some months are very good. They could capture up to 100 kilo fish per boat, but the fishery yield diminishes with time. And also there is a whole period over here where the fishery yield is very, very low. They have no explanation for it. Absolutely no explanation. And there was a total lack of data on plankton production. This is a planktivorous fish. So the production of phytoplankton, zooplankton, should be important, but nothing was known about that. And so that's why I came there. Well, no, not exactly why I came there. It occurred purely by chance. In 1988, I went to Rwanda for the first time to work on a much smaller lake, Lake Mudanças, to help a Rwandan student to do his PhD. And this lake the same problem is everywhere. Report of decline of the fish catches, and we were trying to investigate if this was related to a decline of phytoplankton production. In this lake, there were the night tilapia, which is planktivorous. So something might explain why the fish yield in this smaller lake, Lake Kouazi, was declining. I was working on this lake, but on a Sunday, I went on an excursion on a small lake in Lake Liège, and there I met the leader of the FE project. What I talked about what we were doing in Lake Kouazi, he said, okay, might be interesting for us if you came to Gizeki, the north, where they were operating, discuss with them and see if it is possible to set up a project on Lake Kivu with the hypothesis that maybe it was the production of plankton, phytoplankton, zooplankton, which could explain the pattern of fish yield over 1 year. So this began this way. Well, this was in 1988. I set up a project one day in October 1990. What happened in October 1990? The war began in Rwanda. So I had only a few days to sample the lake, to collect quickly some data, and then I had to stop. I was evacuated, came back to Belgium, and to go back to Belgium, and nothing happened for 10 years. So I went back to my studies. And then after 10 years, I had the opportunity to go back to Lake Kivu because I had a mission on Lake Tanganyika. I had another project starting on Lake Tanganyika at that moment. I used the opportunity of this trip to go back to Lake Kivu and to meet with this man, who is Boniface Kadinkili, who worked on the biology of the liquid sardines. And I had talked with him a lot of time in the 1990s when he was doing his PhD at the University of Liège. So I knew him. I went there to meet him simply at Lake Kivu, and we had the idea to restart studies on the lake on phytoplankton production, zooplankton, and so on. So, when you start studying a lake like that, you're trying to collect the data which are important for you. On phytoplankton production, there are a few data which had been collected in the 1970s by geochemists. Why geochemists? Because they wanted to know what was the carbon production, the organic carbon production in the surface water, to determine the production of methane in the deep water. Another relatively important paper is a paper by Eki and Klink, the Americans. They studied Lake Tanganyika and they did a mission Lake Kivu, Lake Edward, and Lake Albert. So they had a few data on Lake Kivu about the composition of phytoplankton. So there were cyanobacteria, chlorophyll, poison-facade, diatomy, and so on. But these were at that time the only data available on the composition of the phytoplankton. From the Damas mission in the 1930s, there were data that only about diversity of the plankton and the benthos. And for example, Damas was clever enough to collect samples and to send them to different specialists across Europe. For example, the diatoms, planktonic diatoms from Lake Kivu were studied by Ushtet, which is a well-known specialist of diatoms. And so from 2002, we started with two people. We started investigating the phytoplankton, which was our mentor here, for example, and the zooplankton was studied by Pascal Isopichon. So Pascal is from the region, he's from Bukavu. Hugo came with us, of course, there, spent some time, we spent a few years in forming a very nice, very efficient team with Pascal, and they gathered data on the phytoplankton and zooplankton. They used simple boots, and they worked with a team of fishermen. You know, this is Joba here, which is Joba, was the fisherman, and every 2 weeks, we sample the lake, and we see here the smiling Joba. Correct? So, why not? So they were excellent people. In the following project, we also had Rwandese involved, and here is Angelique, who was a master student from Rwanda coming to Namibia. So we begin to set up an interesting team. So some observations. Here, time scale is beginning of 2002, we go to 2005. This is a depth time diagram. Time here, few years. The depth is here. We sampled onto 80 meters here. You can see clearly period of stratification. The temperature is high at the surface, and there is a temperature gradient. So this is a typical stratification period. And from year to year, you can see that there is some variation. The length of the stratification period is not always the same. There is already an interannual variability which is visible. Then you have mainly between May and September, a period where the air temperature is lower, the wind stronger, and then you have a possibility of mixing down to 60 meters. But never below, because there is a salinity gradient, which prevents the mixing to go further down. So to prove that, of course, well, this is obtained, of course, with CT, with vertical profile of the temperature. And here you have oxygen profile to show the variation of the concentration according to them. This is the typical rainy season situation. You see the oxycline, which is located at around 40 meters, while here the oxycline goes down when the lake mixes lower, and then you have an oxycline which is located at 60 meters, and the oxygen is totally zero from there. So there is clearly alternation of period of stratification from October to April, and mixing in the dry season from May to September. This reproduces regularly from year to year, but with some interannual variation. Okay. What does this mean for the phytoplankton? Phytoplankton needs what? Needs nutrients. Okay, CO2, needs nitrogen, needs phosphorus. So you measure, for example, the SRP, the soluble reactive phosphorus, total phosphorus, nitrates, silica. This is not Lake Kivu, this is Lake Tanganyika. The process is the same. So it's typical in any lake, actually. You have in the surface layer, you have the lowest concentrations, and the concentration of nutrients increase with depth. Okay. This is the lymphatic zone. So the zone in which photosynthesis can take place. In Lake Tanganyika, it's about 40 meters. And this is the variation of the depth of the mixed layer. So what does this mean? If during the rainy season, the depth of the mixed layer is about 20 meters, for the phytoplankton, which is transported in the water column, it means that most of the time the phytoplankton is receive a lot of light. This selects for what? For energy, for cyanobacteria, which can stand very high light. So it's favorable to photosynthesis. The problem is in this layer you have very low nutrients. So in this situation, in the stratified in the rainy season, you have conditions of very high light, but nutrient limitation. When the lake mixes down, in the Lake Tanganyika, you're down to 70 meters, for example, the phytoplankton is transported to depths where the concentration of nutrients are larger, but it receives much less light. So there is a shift in the mixing season, in the dry season, from nutrient limitation, high light, in the rainy season to light limitation in the dry season. Right. This is a situation that you observe in temperate lake in summer, so it can be considered that tropical lake you have endless summer. But you have to take into account that these lakes are very deep. They have very few tributaries, which do not represent a very large input of nutrients. So all the processes which maintain, which explain the concentration of nutrients depend on internal loading, internal processes. So the mixing processes in the lake. So Lake Kivu, the lymphatic zone is about 20 meters. There is a variation of the mixed layer, I have already commented that, and the very long rainy season, high light exposure, but nutrient depletion. In the shorter dry season, lower light depletion, higher nutrients, and of course, can be compared to the temperate lake in the spring and in summer overturn. And the phytoplankton response, but you can see it. Examining the sample, you expect to have seasonal variation of biomass and taxonomic composition. For example, you can measure chlorophyll. You know that chlorophyll is a proxy of phytoplankton biomass. Here you have record again its depth down to 60 meters. Time, so several years from 2002 to 2008. You can see clearly periods when chlorophyll is low, it usually corresponds to the rainy season conditions. Phytoplankton doesn't grow much because there is nutrient depletion, nutrient limitation. While at other moments you have higher chlorophyll, and this usually corresponds to the mix, to the deep mixing of the dry season, with exceptional year, the year 2008, for example, presented a huge peak of chlorophyll. You have the scale of chlorophyll concentration here. The blue is below 0, the red is above 5. And even in a mixed season, for example, you can have sometimes small peaks of chlorophyll. This corresponds to storms because the lake is surrounded by mountains. This creates a climate, a regional climate, where storms can be very important and induce a short period of mixing in the lake. This is a database which is quite unique for a tropical lake, actually. You very rarely have a time series as long as this one. These data have been available on the website, on the repository, the data repository of the GREON network, which is the Global Lake Ecological Observatory Network. So anybody can use them, actually. So if you look at the composition, I will not insist too much on that topic, but the main groups are diatoms in here, yellow-brown, cyanobacterial blue, diptophiles in reddish. Period of rainy season, nutrient depletion, especially, for example, nitrogen depletion, are good periods for cyanobacteria. Period of mixing are generally marked by peaks of diatoms, with lots of variability from year to year. This is determined not by microscopy, but by HPLC analysis of marker pigments, which is an advantage for the database because the method used is always the same. It's a machine which measures the phytoplankton extract acetone. So when you make chlorophyll extract, you can use the extract, analyze it by HPLC, measure the different pigments, which are mainly carotenoids. These carotenoids can be used as quantitative markers for different categories of algae of phytoplankton. But it's useful to make microscopy also. It's mainly Hugo Sarmento, which did the microscopy of these algae. I see him smiling. He's providing a lot of things. Well, you have phytoplankton here. This is a picture under fluorescent microscopy. Other cyanobacteria, standard microscopy with an enterocyte here, which shows that there is nitrogen fixation. Dinoflagellates, diatoms. Many diatoms are long shaped each year, etc., etc. So I will not insist on this aspect. If you're interested, you just ask Hugo Sarmento to show this publication of 2007. Okay, what about the explanation? Well, we started with divide. We are going to try to explain the variation of the catching of the sand bazar according to the plankton, to the plankton species. The advantage of ABLimno is that the system is very simple. You have phytoplankton, zooplankton, only cyclopoid copepods, 2 herbivorous species, 1 carnivorous species, some rotifers. So you expect a coupling between phytoplankton production and zooplankton production, and that's what happens. Here you have phytoplankton biomass, so the balls and the line. Okay. First year you have a peak of phytoplankton in September, for example. Second year, the peak is observed in July, August. very quickly a peak of zooplankton biomass occurs in a matter of 2 weeks. Okay, and then it goes down because the phytoplankton resources are progressively depleted. It's a very classical, well, predator-prey interaction. And if you follow the catches, well, you can see that the people there tend to think that the catches go up again with the rain. But the rain come back. When does the rain come back? Here, in November, December, and so on. But this corresponds not to the rain in itself, of course. It corresponds to the availability of zooplankton, which is consumed by the fish. Actually, it has been established that the fish reproduce all the time. So there are cohorts of small sardines which are produced all over the year, but they don't find food all the time. And that's why you have a fish stock today which decreases all over the rainy season and which begin to increase again after the dry season, after the phytoplankton and the zooplankton peaks. Another problem of lake is that, well, it could be influenced by the activity, the volcanic activity, which is still important. The Nyiragongo volcano, for example, has a lava lake. This is a picture that I took myself in 2015. This is the lava lake inside the Nyiragongo volcano, which shows that these two volcanoes are very, very active. And it's also a killer lake. It's still presented like that, by comparison with another killer lake, which is much smaller, located in Cameroon. In 1986, there was what is called a limnic eruption. The gas, well, this lake Nias is also a lake which accumulates methane and CO2 in its deep waters. And there was a landslide simply, which provoked a full mixing of the water column and liberated CO2, which was in the bottom water. It came to the surface, leading the eruption. That's exactly the same process. When you open a bottle of champagne, there is a high pressure gas dissolved the liquid. If you diminish the pressure suddenly, you have an outburst, you have a production of bubbles. This is the same phenomenon. Here, the CO2 accumulated in the bottom of the lake was liberated in a few moments, and then it asphyxiated the people and the cattle and so on in the village below, because CO2 kind of flows on the land. And so you can imagine if a similar phenomenon occurred in Lake Kivu, concentration of CO2 are enormous. Concentration of CO2 is 300 billion of cubic meter. And there are 2 billion people living around the lake. So the question is, could a similar phenomenon, a similar catastrophe occur in Lake? At the present time, the reply is no, provided that there is no catastrophic volcanic eruption. A volcanic eruption would liberate, maybe if it occurred in the bottom of there are volcanoes also in the bottom. The volcanic activity provoked an eruption there, could be an eruption. But anyway, another reason for an eruption, limbic eruption to occur, is if the gas concentration increases, the gas could reach saturation, and then it's exactly the same phenomenon as when you open the bottle of champagne. It could form bubbles of methane in which CO2 would be trapped. And that could provoke a catastrophe around the lake. So the idea came to exploit the methane from the bottom waters. How can this be done? And it's presented like a win-win solution. Because with the methane, you can use it for production of energy, and at the same time, you would, over time, decrease the concentration of methane and of CO2. You will progressively decrease the lake. How is it done? You construct a floating platform. You put a tube which goes to the bottom, and you simply pump the water up, and with the diminishing pressure, there is a degazing. So you get a mixture of gas, CO2, methane, hydrogen sulfide also, because it comes from an anoxic bottom. And so if you separate by different processes, methane from CO2 and from sulfide, you can, with a pipe, you can conduct the methane in an electric power plant, and you produce electricity. At the same time, you contribute to decrease the gas concentration. But you have different problems. What do you do with the water which is displaced? If you remove, you cannot put it back in the surface water because it's very saline. It contains a lot of nutrients. So you will transform the surface water in such a way that the ecosystem will be totally destroyed. So another reason why you can do that, because if you remove the salt from the deep waters, you will change the salinity gradients. The salinity gradient keeps the gas down there and prevent the eruption. So what you have to do, if necessary, is to send back the biggest water where it comes from. So if you pump from 300 meters, you have to get it back, you have to put it back to the sediment in order to keep the salinity gradient. It's absolutely necessary. There are a lot of details which, a lot of measures which are necessary to take into account and to apply to avoid that the exploitation of the lake would create even more dangerous conditions. There is another problem. There is washing water. The washing water is water from the surface, which is used for cleaning the gas, because the CO2 dissolves in the surface water, while methane, which is not that soluble, is separated. So the surface water is used for separating CO2 from CO2 and hydrogen sulfide from the methane. And this washing water must be released somewhere, and it is normally it should be released at the bottom of the big solid of the biosphere. Well, this is done. So a plant which produce about 25 megawatts of electricity, is operated from the end of 2015 on Lake Kivu. It is the Kivu 1 project, which is presented here. So if you go to that to the site, you will have a few details, well, quite a few details about the operations. At the same time, they have to monitor the lake. They have to monitor the change, which is imposed by what is called the management prescription, a series of regulations which are supposed to be observed by the exploitation. And so they have to monitor any limnological change which could occur in the surface water in the deep waters. They follow the concentration of methane in the deep water, so they have to do all kinds of monitoring. But this occurs on the Rwandese side. So the Rwandese authorities are also interested in monitoring because if the monitoring is done by Kivu himself, it's an auto control. But it's better to have an independent control, and the Rwandese authorities wanted to do their own monitoring. One of the elements about among the areas to be monitored is, of course, phytoplankton. Because if, for example, nutrients are released by methane exploitation, you will see it immediately, because most of the time there is nutrient depletion. Any input of nutrients in the surface water would cause a phytoplankton. So the idea is that if you control the phytoplankton biomass, you will have evidence that there is something wrong with the exploitation of the methane plant. And so we proposed to set up at the end of a project, the project which finished in 2008, we proposed to establish the baseline of Lake Kivu based on limnological observation, but mainly also on the phytoplankton biomass and composition. And we collaborated with LKFP, with the Lake Kivu monitoring program. These were people who worked with us there, my technician Bruno, and Rwandese technician Edouard Rouget. You see Edouard here on the boat, and behind there are the volcanoes and the first methane exploitation plant, which was experimental, which was called KP1. Okay. After that, after the start of Kivu exploitation, so Kivu started in 2015, the baseline was done, so we had baseline data. But I was also involved in a project financed by the Dutch Corporation to develop the capacity of the Rwandese from the Lake Kivu monitoring program to control them themselves, to make the analysis themselves. So what occurred before we took the samples, we extracted the pigments in the field, transported back to Belgium, and everything was analyzed in the overlap in Belgium. They wanted to do them themselves. Okay, so they applied for funds to the Dutch Corporation, and they got the possibility, they got funds to buy a full HPLC system that I contributed to install on their monitoring station on the shore of Lake Kivu. And so they started again themselves to study phytoplankton environments and composition using the marker pigments. So some people from this lab came to Belgium for training first on my system, and then I came there to install the new system and to help them starting the machine and getting their first data. So I couldn't prevent myself, keep myself to show you avatar, which is the kind of thing that you get with the HPL system. So you have the different pigments. This tells me that there are diatoms, because there is phytoxanthine. There are cyanobacteria, because it's an important pigment. Zeaxanthine is an important pigment in cyanobacteria. There are very few chlorophytes. Within chlorophyll natural for chlorophytes, and all algae have chlorophyll. So the largest peak is chlorophyll. So looking at a chromatograph table like this, I can tell you the composition, not quantitatively, but this can be determined by computing using a program that is called Syntax. So, if we collect all the data, which is, this is chlorophyll, microgram per meter chlorophyll, you have a scale up to 8 here, starting 2005. This is on the wattage size, on the country size. We started in 2002. It was a bit later on the wattage side. 2005, and with some gaps, we go to the end of 2019. So you have several years. So what do you observe? At the time when Hugo Sarmento worked, this period here, chlorophyll didn't move much, a little bit more during the dry season, a little bit less during the wet season. Everything was expected. Below you have green algae only, so the contribution of green algae to the chlorophyll. At that time, I don't know, green algae, few of them. So at the end of the PhD of Hugo Sarmento, we were convinced that chlorophyll were almost upset.
Glorifies.
Glorified, sure. So green algae were almost upset. But what do you observe in a longer period of time? Oops. Well, this is when our monitoring of a baseline begins. This is the beginning of the operation of kilowatt plant. Before kilowatt started, biomass and green algae became. That was unbelievable, according to what we believed about the composition that we had observed from the composition that we had observed before. And so this means that if you want to establish a baseline on which to assess any trouble from delay caused by the methane utilization, you have to have data for a very long period of time, because something happened here, and this can be explained only by a change in weather pattern. We established, looking more detail in the composition of the species and so on, we established here that there were much more frequent mixing, much more frequent with even, which allowed partial mixing of the water column, which helped these green algae, which are not motile, to remain suspended in the water column. And that's how they were more successful. If you look at the other groups, already present here, but they clearly contribute to the increase of chlorophyll, increase of phytoplankton biomass, while the cyanobacteria, which are normally more important in a stratified lake, began to decrease. So there is this is the evidence that there is much more mixing in the lake, and this can be related to a change in water pattern, where measurements, very high resolution measurements of the temperature of the water color, which show that there were mixing every day on 10 meters of air, and this was sufficient to maintain this normal hierarchy in suspension. And the cyanobacteria lost their advantage, for example, being able to float better than the other ones. So they lost the competition. So the conclusion is changes phytoplankton are related not to methane expectation, certainly. And a study made by collaborator at the time, François Lachambeau, with no working actually for Kivu, for the monitoring of limnological and planktological change for Kivu. He established teleconnection with the temperature, the surface temperature of the Indian Ocean. Here you have an index which depends on the variation of temperature in the Indian Ocean. And this is, each dot is the maximum chlorophyll of the dry season. There is a clear relationship between, so an index which is determined in the Indian Ocean, and finally the productivity of the lake. So this is an evidence of a global influence of changes which occur at a global scale, changes, climate changes which occur at a global scale have an effect of the productivity of lake. Here, another relationship, again, is the dry season chlorophyll peak, which depends on the stability of the preceding rainy season. When the preceding rainy season, when the Schmidt stability index, which depends on the temperature gradient, is weaker in the it's weaker in the rainy season, you get a much higher dry season peak. But it is more prejudicial, it takes less energy to mix the water column, and so the mixing can occur at greater depths. And then you get a larger chlorophyll peak. Okay. There are many other results about the studies we made in Lake Kivu. One of these results is to look at the way the carbon taken up by the phytoplankton can be used in the food web. If you look at the production of phytoplankton, this is the gross production. The particulate production is here. Part of the production is dissolved production, carbon which is excreted by the phytoplankton, which is used by the bacteria. There is some production of bacteria which are methanotrophic, using the methane which diffuse from the waters. If you look at the link, the main thing here is that you look at the link between particulate production of the phytoplankton and zooplankton production, you have something like a 10% transfer between a 10% ratio between phytoplankton production and zooplankton production, which is what you expect. A 10% transfer efficiency is observed almost everywhere. But if you look at the transfers from zooplankton to fish, it's much lower. It's not 1%. And so this is the proof that if the fisheries expert, they always expected a higher sardine production in Lake Kivu than what they observed. So it's not the same as in Tanganyika, where this species exists. In Lake Kivu, they had much lower fish production. The stock and the production of fish is much lower than expected. Here we prove that the problem is not at the transfer from phytoplankton to zooplankton. This was the hypothesis by people who said the sardine would deplete the zooplankton. At one moment, zooplankton will be totally depleted and the fishery would collapse. The fishery has not collapsed. We have other data based on the hydroacoustics. We did the hydroacoustic survey all over the lakes. The stock of the sardine has remained with some small variation to be considered as remain the same over 30 years. So no particular effect. So if the fishery yield in Lake Kivu is lower than Lake Tanganyika, for example, it's not because there is not enough zooplankton. It's just because there is a problem for the fish. Actually, so the explanation might simply be that this fish is a visual predator. The water transparency is Lake Kivu is not the water. When you look at the hydroacoustic diagrams, you see that the fish are located the first 30 meters. Below that, it's most of the time anoxic. So they cannot go further down to feed. And because the water is not that transparent, well, they feed efficiently only maybe the 21st meter of the big stream. This is maybe the main explanation why the fish productivity, the sardine productivity, is not as large as in Lake Tanganyika. But anyway, some people say, well, it would be good to have more nutrients in the biome, in the surface water, because you would increase phytoplankton production, that zooplankton production would increase, and sardine production will not be the case. Will not be the case. What you would get simply is a reduced zone in which the sardine could live, because the lake would be eutrophied. You would have more. You would increase the layer in which the water is anoxic. So you would destroy the lake, and you would destroy the fish. Okay, now, if you're interested, there is a book about different topics on Lake Kivu. But if you're interested in learning more, of course. I wanted to say some words about the productivity of Lake Tanganyika. So, Lake Tanganyika is remarkable by size, by depth. It's the second deepest lake in the world after Lake Baikal. So the maximum depth is about 1,500 meters. Contains about 18% of the fresh surface water on Earth. And there's the productivity, very productive fishery, which is comparable to marine fisheries. It produces around 200,000 tons of fish per year. So it's also known for other things, for its large diversity of fish. But this diversity is located across the world only. Many endemic species. So two species are mainly used by the many captured there. So another endemic sardine, which is produtividade, which is called afeta locally. Afeta can be dried, so it can be transported to other places for commercial exploitation. So this species, which is the predator of the sardine. So this is a very simple scheme of the food web of the lake. So the predator, the plantivores, the plankton, phytoplankton. But in reality, it's much more complex food web than that. So the main problem here is the increase of the temperature of the lake, which has been shown by Pierre Descy in a paper of 2021. So he collected data of air temperature here, and he was able to correlate this increase with decrease of the fishes. So there is an hypothesis that the productivity of the lake is influenced by climate change. It has been published in many papers, many important papers in nice journals, Nature, Science, and so on. And one proven that climate change decreases aquatic ecosystem productivity of Lake Tanganyika. And one of the consequences is the fish catches are also declined. But this is challenged. This is challenged by the team of scientists who worked on Lake Tanganyika in the 1990s. They, contrary to this evidence, in the paper that I presented before, they support the idea that the fish catches depend on just changing fishery practice, for example, increase of boats, increase of fishermen, and so on, not climate. And so there was a long debate about that. And as we worked on Lake Tanganyika, we worked with the idea that Lake Tanganyika is influenced by climate change. We had a project which was financed by the Belgian Policy Office in a program which was called Sustainable Development. And this project was called Climate Variability and Superability Lake Tanganyika. So in the framework of this project, we had the possibility to make monitoring of limnology and plankton at two sites, Tanzania and Kigoma, and in Punugu in Zambia. We organized also cruises in a boat which is called Maman Benita, which is unfortunately disappeared. Now it's sunk on the lake, but it was used several times for scientific expeditions. And this Clean Lake project was followed by another project called Clean Fish, still the same team, of course, where we used especially satellite images of the lake to study sulfur temperature and to determine chlorophyll. This is a large lake, which is submitted to influences of the wind. The main cycle, the main influences of the wind are summarized here. We started in the rainy season from January to April. At this time, the air temperature is high, you have less wind or no wind, and you have stratified conditions, stable conditions all over the lake. From the beginning of May, the southeastern winds begins to blow. They push the water from the south to the north, and this provokes an upwelling of the nutrient-rich water to the surface. You expect that this upwelling will result in increased phytoplankton productivity. When the wind stops, you can have the water coming back to the soil. There is an oscillation actually of the thermocline, and you can have a secondary upwelling in the north. It doesn't occur very often, but it can. And after that, you have still some oscillations of the lake, which dampen over time. And this causes internal waves. I will show the effect of internal waves. So this is a satellite image from Lake Tanganyika in July 2002, which shows a very large heterogeneity between the northern basin and the southern basin. Some deep water coming to the surface. The temperature is about 21, 22 degrees. The blue here it is 28. So you can see here that when the northern basin remain stratified, you have relatively complex patterns of mixing in the south. So this shows the heterogeneity of the lake. And you see what the blue here shows the upwelling which is occurring in the south. If you make CTD profiles over several years, for example, twice monthly, from 2002 to 2005, you have that type diagram, and you can determine the periods of stratification with a higher temperature at the surface, the thermocline. And what is visible here is these oscillations. These are the signature of the internal waves. So the internal waves are generated by this tilting of the thermocline, which occur, as I showed, after the upwelling, and they are maintained and then over time. They are important because they will increase the transfer by turbulence created. They will increase the transfer of nutrients through the thermocline. Here you have the situation observed in Zambia, in the southern tip, and you can see the effect. You can see clearly the upwelling, and you can see that there is variability in the upwelling intensity. It was very low here, and it was much more important. Okay. Well, here you have the air temperature, wind speed, different times from 2002 to 2006. The water stability, period of mixing, and the rainfall here, so this classical scheme you have the stratification taking place in the rainy season. Here you have the peak of phosphorus, for example. Well, the time scale is not the same, 2002, 2004. You have a peak of phosphorus, which is favorable to phytoplankton productivity, of course, in the dry season. And here you have the response of the phytoplankton in terms of nutrient content. It's the C2P, the carbon phosphorus ratio in the phytoplankton, in the system, which can be used as an index of nutrient utilization. So clearly, when phosphorus increases in the dry season, you have sometimes moderate or no nutrient utilization. So this is favorable to production. So what I would like to discuss here is simply the differences in chlorophyll concentration and primary production observed in the 1950s by Descy et al. And in the 1990s. So these were the guys who presented actually that the primary production had not decreased, but it had increased actually. And that's why they prefer the hypothesis that the fishery did decline because the fisheries practice changed. But somehow we had to examine it. And so we started looking at chlorophyll estimates by remote sensor using a sensor which is called body sampler. So we have, for example, here an image of the lake with the chlorophyll concentration. Some areas have high chlorophyll, relatively high, about 2 to 3 microgram per liter, while other zones are extremely poor in the phytoplankton. But there is a lot of heterogeneity. Analyzes many images over several years. There were 3 years available here. We were able to show that actually the lake is very heterogeneous, as suggested by the former events. This is a synthesis from the 3 years, which shows that the lake should be divided in 13 different regions according to the covary chlorophyll concentration, with the highest concentration. Well, first region here, so it shows simply the very large heterogeneity as concerned phytoplankton. From this study, we were able to determine primary production of the lake. So we used a combination of satellite data and field data to calculate primary production, using, for example, the photosynthetic parameter, the photosynthetic response of the phytoplankton measured in the field using C14 incubation. So we were able to determine primary production. If you look at the figures here, they are not extremely visible, but you have, for example, in green, something like 800 milligram carbon per square meter per day, and other regions are much poor. We expect that from the difference in stability and mixing processes. So the poorest regions are in the north and the richest regions are in the south. So if from that, come back to the comparison of chlorophyll data. So the studies from the 1950s showed this range. from the 1990s, the dead threat, which is quite comparable. Well, nothing is clear for that. The ribbon sensing data showed even a larger range, just because what you see is only the surface water. What you see here, for example, 25 microgram per liter is a surface blue outside the water. So from that, you cannot tell much. So any change, it is difficult to say because there are changes in sampling designs. There are differences in sampling design. But if we compare primary production studies, we get those things. And the primary production estimated in the 1990s are still higher, but if we remove what they observed in the northern part of the lake, which is more productive, we finish with data which are similar, which shows indeed that there was a decline of primary production. So there is probably a change. So our conclusions were that primary production in Lake Tanganyika declined of about 15% since the 1970s. Are there consequences for the food web? This is difficult to say because it's a complex system. It's a complex food web, but it's likely that the phytoplankton community changed. But we don't have long-time series, so it's very difficult to compare what was observed in the 1970s, 1990s. It's always the same. You would absolutely need long-time series to say something with some certainty. That's my main conclusion for these studies. So I looked a little bit at more recent literature, using, for example, remote sensing for estimating primary production in Lake Tanganyika. Here, this is a paper devoted to estimating primary production from satellite images, algorithms, and so on. Something quite relatively recent. They studied primary production in North American lakes, the Great Lakes of North America, and they included Tanganyika. They find exactly the same thing as we observed. A decline of the estimate of 16%. Another research, quite interesting research, based partly on our data, is a modeling research. These guys developed a 3D model of the lake. This is the above here. This is the present situation. So this is simulation by a model which simulates the hydrodynamics of the lake. The simulation of the temperature. So in March, you have a typical rainy season situation with the surface 28 degrees, and you have a temperature gradient, and you end up at 24 degrees at a depth of 150 meters. In September, they simulate quite well the opening in the north, in the south. So this is the southern part, this is the northern part. In September, the opening occurs in the southern part, while the north remains stratified. And you have the accumulation of the warmer water in the south, which creates a stratification. They simulated the future situation using a climate change scenario, which is the worst. Okay? In the worst scenario, they observe this. They observe that the lake will heat up, of course. You will have in March, in the rainy season, temperature of about 30 degrees. The bottom water will also increase, but more slowly. So the gradient will not really be affected. Actually, the stratification will be increased. Okay, this will create, you can expect, more nutrient depletion and probably less plankton production. Simulation of the September shows that the period in which the rain will occur will be reduced. So they showed actually that the global warming will certainly influence the hydrodynamic of the lake in resulting in probably decreased productivity. So, my last point. I use the data simply to provide to large groups which want to make global comparison. They are included in GLEO, for example. Here, it is a contribution to the storage project. The storage project is based on the stoichiometry of different ecosystem compartments. Stoichiometry is the elemental composition of phytoplankton or plankton. It is used also for animals and so on and so on, land animals. But this is devoted to aquatic system. And this is to show that what is the contribution of the main contributions. So they are for at least temporal series of 3 years. Okay? We had system stoichiometry analysis for Lake Tanganyika and Lake Kivu, and we provided some point for Africa. But you can see that in Africa, there is not much. Similarly, in South America, there is not much. So it shows that there is something to be done. I think if you have data, I think you should contribute to such studies. For some reason, you were not contacted. We don't know why. We had a question yesterday, we had no idea. But I feel that you certainly have some groups which can contribute to that. Another database we contribute to is one of the black is that the SIG project, which is using zooplankton as an indicator group, indicator of change. Anything actually. For this project, there are several ideas, several followers project which have been developed. And again, you can see that in Africa, 2 points. Lake Tanganyika, Lake Kivu, at least 3 years of data. Okay. In South America, one not. For why, I guess that there are some of the data which could be exploited, included. Okay. I have not replied to my initial question, but could be discussed. There is, of course, evidence of weather patterns, climate change, or the productivity of these lakes. I could have talked about Lake Victoria, for example, we observed also change can be related to change in weather patterns. So I just wanted to pay tribute here to people who have contributed to these things. Here these are people from the Lago Tanganyika, Jean-Pierre Descy, for example. This guy is Ismail Kibire, who became the director of the TAFIRI, the Tanzanian Water Authority, research institute. Other people. This is the girl who introduced me to research in Africa. She's called Rose Conservation. I went to us. So I already mentioned Boniface Kadimkini. Here is Georges Arenga with the technician Clermont, conservateur again. François Archambault, Martin Schmidt, the geochemist, and Pascal Ichoukiso, the geoplanetary specialist. Bruno, certainly a good technician which has been involved in the two projects, like Tanganyika and Lago Kivu, and many other people working in Tanzania and Zambia, including girls, were involved. And I didn't talk about the microbiome. The guys studying the microbes, using flow cytometry, making some the first molecular analysis and so on, with Anna Coutin, Stéphane Stubit, Hugo Sarpentier, Ted Gasol from ICM in Barcelona, Fernando Rey also came to my lab for some months also. And finally, thanks for watching. Thanks for your patience. Much too long. Sorry for the hesitations. I'm not used anymore to this kind of approach.
There are questions in the room or in the chat? Yeah. Any questions here? Yeah,
Thank you very much for the talk. Very inspiring. I have a question actually about Lake Kivu.
Yes.
I was very interested when you showed the food web and how energy flowed from the phytoplankton to the plankton and then to the sardines. And I wonder if there wasn't a pressure from the management or population to introduce new fish species.
Excuse me?
To introduce more fish species. Because if you show that the sardines are not efficient, then maybe other species.
Actually, when the small sardine from Lake Tanganyika was introduced, the idea of the Belgians was to introduce the predators. But I think that fortunately they did not succeed because they believed that they could reach the same sardine production as in Lake Tanganyika, but it did not occur because the lake is so different that is not possible. That was my point. The 10,000 tons of Sambaza per year is about the maximum that this fishery can make. And that's for many reasons. One of the reasons, I think, is also the fact that the nutrient depletion during the rainy season of the phytoplankton influences zooplankton growth. You know, this is related to the stoichiometry, in fact. I don't know if you know something about ecological stoichiometry. But, okay. You know that richness phosphorus of the phytoplankton influences zooplankton growth. I think it's one of the reasons why I did not compare the phosphorus content of phytoplankton in Tanganyika and in Kivu, but phytoplankton of Kivu is much more nutrient depleted. So it's less favorable to zooplankton growth. It's one of the reasons, but the people who introduced us on Baza didn't know that they had absolutely no knowledge about that.
Okay. Does it mean that the fish have treated lots of zooplankton to grow, and accumulate?
Yes. My point is also that maybe they can't. One of the first sampling I did in October 1990 in Lake Kivu was to make profiles of zooplankton, vertical profile. What we saw is that the copepods, the females bearing eggs, were located only at the bottom, at 50 meters. At 50 meters, there is no light.
The bottom of the mixolid.
Right, the bottom of the mixolid. Yeah, okay.
There is no light. So the sardine evolved in a very clear way.
Okay. At 40, 50 meters, there is no light. There is no way the fish can catch the plankton because they are visual predators. They have to see their prey. And that's one of the other reasons. In Lake Tanganyika, the water is much clearer. So plankton can migrate down to 100 meters in one day, and then migrate up at night. The predation efficiency of the fish is much better.
There is also oxygen below the thermocline in Tanganyika.
Yes.
It's not totally anoxic suddenly. So.
Well, that
is another niche, And the sardine evolved there, so.
That's also a difference between the two lakes. The mean chlorophyll in Lake Kivu is something like 2.5 microgram per liter. So it influences the water clarity, of course, but also the biome. While in Tanganyika it is less than 1. So,
other questions? I think there's in the chat.
There's a question here in the chat. The question is, how do natural lake dynamics and human-driven environmental changes in East Africa jointly influence the persistence, transport, and infection risk of waterborne diseases? Yeah.
I'm afraid I can't reply. Sorry.
I remember some studies on cholera with plankton.
Cholera. Yes. There was a project. This year also. They had correlations between copepod biomass and
cholera.
Right.
Because the cholera lives in the attached to the plankton, something like that.
I examined the report. It was not convincing. They could not reach definitive conclusions about it. It was an hypothesis, but for me, it's not verified.
They might be.
And they tried to do the same in Lake Kivu. I discussed with the girls who was making a master project on that, but they wonder if it was possible to use our data to make a similar study. But I referred to this Celtic project, and I said, okay, just give up. There is no definitive conclusion.
I think there's another question.
Yes.
Thank you. I would like to ask, you showed that the fish in the type of decline over the years.
Yes.
But do you know why the hippos
Okay. The hippo decline because the hippos are located mainly on the Congolese side. It is normally a natural park.
but there is a lot of poaching there. But there is a lot of unrest. So it's like the uncontrolled mining in Congo, which is a very large problem. So it's mainly peoples were killed by poachers, mainly for the meat, but also for the ivory of their teeth. This is valuable. It could be
No relation between fish and meat.
what?
No relation between fish.
Yes, there is a reason. The reason is that basically the post transfer the nutrients from the land because they graze on the land. They come to the lake, and their feces enrich the lake in nutrients. So they just transfer nutrients from the land to the lake. If the population decreases, it is expected that the nutrient status on the lake will also decrease. So what we observed in our data, for example, about phosphorus, it seems that the amount of total phosphorus in the lake was divided by a factor of 2 between the 1960s and the 1920s, the 2020s.
I think there is another question online.
Yes. The question is, your long-term data on primary productivity, phytoplankton, and nutrients from African lakes are fascinating. In addition to the overall effects of climate change, have you observed any impacts of cyclical El Nino and La Nina events? I'm especially curious about their influence on algal blooms, even under conditions
I
of low
think
biomass.
this remains to be done.
Yeah.
This and that's why this is not the kind of research I'm able to do myself. And then that's why I tend to provide my data to anyone who wants them. So if somebody is interested in making this link, this analysis, I would be happy to provide the data. No problem.
I think for
I have done it with Gleon. I can do it. Well, all the data are already on data repository in Gleon. So if someone wants to study with more detail, okay, these processes, they can use the data. If they don't have enough, they can ask me. No problem. I will provide it freely and with great happiness.
Okay, I think we can close. Thank you very much to all of you. Thank you, Jean-Pierre. I hope you come more often. And you will be here for the next 2 weeks. So if you want to come to the lab, talk to me, well, plenty of time. Thank you very much for your. Obrigado ao pessoal que estava na reunião e perdão pelos problemas na transmissão. Obrigado, Pedro. Thank you.
Okay.
Marcelo. Actually, I have one question.
Yes.
You said